each lecture. And with that being said, we're very happy to have Rylee Lyman tell us about action on trees, group acting on trees. So whenever you're ready, Rylee.
Great, thank you. And thank you for coming back to our second day. So, let me begin by putting the links for the slides in the chat. That will be helpful. Let's see, so here, great, so here is the link to the PDF coming at you now. And then if you happen to have Notability and you wanna like use my notes as like a worksheet, there's that as well. I don't know how that works, so you'll have to figure it out. So today, I guess, right at the end of yesterday, I stated the main theorem of Serre theory. And we're not going to prove this main theorem, but we are going to get a feeling for like why it's true and how to work with it. So that we're going to construct the tree that our fundamental group will act on, and we're going to construct the fundamental group as well. And we're also going to get some intuition from these things called graphs of spaces. And then we'll do some examples. We'll draw some pictures. We'll compute some group presentations, and then right at the end, if there's time, some stuff that I do in my thesis, really building on work of Haken and Bass, is like covering space theory for graphs of groups and morphisms of graphs of groups. Those are just things that I think are cool, but be aware we'll have to see a little bit more category theory. But it'll be fine. Great. So let's dive in. So yesterday, our theorem said that if you have a graph of groups and a base point, then there's a group G, which is the fundamental group of the graph of groups based at the point P, and there's a tree T. This is usually called the, I guess, the Serre tree. But you could also call it the universal cover of the graph of groups if you would like. There's a tree, and then G acts on the tree. And remember yesterday at the very beginning, we talked about the notion of a quotient graph of groups. I guess that was at the end, actually. But this action of G on T induces the correct graph of groups, like the one that we started with. And then just for some notation, if I have my tree T, then the natural quotient map I'm going to call pi. Great. So first of all, even if we just sort of accept that the theorem is true on faith, we can use our favorite thing from studying group actions, which is the orbit stabilizer theorem, which is like, I don't know, the most powerful thing that you learn in your first algebra course. And what it says is that if you have a vertex V of your graph gamma, then it's at a lift, so a vertex V tilde in T that projects to V, then what we know is that the set of vertices, such vertices, is in bijection. I guess I'll even upgrade it. I'll say G equivariant bijection with the set of left cosets of G with the group for G, so G sub V, our group that we defined in our graph of groups definition. Okay, that's great. Similarly, actually, there's a similar statement for edges. It says that the edges in the tree, I guess projecting to a given edge E, are in G equivariant bijection. So in G equivariant bijection, great, with the set of left cosets of, well, I guess it turns out to be, maybe I'll write a thing and I'll be willing to be wrong. So I'll say this, so that the image of your edge group in the vertex group associated to its like terminal vertex. That's what I'll say. I'm willing to be wrong about this. We'll probably see later on in the talk whether I'm right when we do some examples. So what Serre in his book called Trees does is he constructs the graph of groups, the fundamental group of the graph of groups first, and then he constructs the tree using this orbit stabilizer trickery, and then we prove that it's a tree. I think that that's sort of, I don't know, it's fine, and it lets you sort of see very quickly what the action is, but it doesn't really give you any feel for what's going on. So I prefer if we construct the tree first and then construct the fundamental group. So that's what we're going to do. Great. So, but first I need to tell you how to talk about things. So we're going to fix our graph of groups, and we're going to pick a vertex. And I'm going to write the star of our vertex to be the set of oriented edges with terminal vertex equal to our fixed vertex V. So for example, in this graph right here, just this loop, the star of V has two oriented edges. It has E, and it has E in the opposite orientation. Okay, so that's our star of our vertex. And what I want to observe is that if the group G and the tree T exist, and we have a vertex V projecting to V, then the star of V tilde is in G equivariant bijection with the following set. Okay, it's going to be scary, but don't worry about it. It's going to be the disjoint union over the edges in the star of V, so the edges downstairs, and the set will be, I guess, the set of left cosets of, yeah, G of V, with the inclusion from the edge group E into G of V, and then I guess just because it's a set of edges, we're going to include the edge. Okay, so this is kind of scary, but all this is really saying is that if we had our tree already, then we know that the stabilizer of our vertex V tilde is isomorphic to G sub V. And we know that the stabilizer of an edge E that projects to an edge downstairs, we know that that stabilizer is isomorphic to G sub E. And that this iota sub E is the inclusion of that stabilizer into the stabilizer of the vertex. And so just the orbit stabilizer theorem pops this fact out for us. So we're going to cheat a little bit. What we're going to do is we're going to build the tree by forcing this observation to be true. And it turns out that's going to be good enough. So we're going to do it in 3 steps. I'm going to show you some of my favorite graphs of groups, and we're going to build the tree for them, and it won't be that scary. Okay, so let's do it. So there are going to be 3 cases. The first case, our graph gamma will be itself a tree, and each of the edge groups will be trivial. Okay, I guess it turns out, I'll just say in words, that our fundamental group will be the free product of the vertex groups. Okay, anyway, but you don't have to believe me. I'll tell you that again later. So this is one of my favorite graphs of groups. This is like closely related to a group that I really like cut my teeth on thinking about. So what we're going to do is we're going to build our tree inductively from copies of our graph gamma, and we're going to force at each stage the observation that we made on the previous slide to hold. Okay, so let me just draw my first copy of gamma. So we have a red edge, and I don't know, I'm doing orange second, an orange edge, and then a blue edge, and then a green edge. Okay. So now I'm going to check at each of the vertices if the condition is satisfied. So first of all, at this vertex, the condition is satisfied. This vertex has trivial vertex group. So the condition is just, vacuous there. Okay, so I don't have to worry about this trivalent vertex. At this vertex right here, I seem to be missing an edge, right? Let's go back and like parse into English what the math on the previous slide said. Okay, so it said that the set of vertices, sorry, the set of edges incident to my vertex v tilde should be in bijection with the set of cosets of the vertex stabilizer, of the inclusion of the edge stabilizer into the vertex stabilizer. So in this case, the vertex stabilizer is a cyclic group of order 2, and the edge stabilizer we've already said is trivial. So the fact that I have one incident edge is bad. I need 2. Okay, so what I'll do is I will create a copy of gamma, and I'm just going to glue it in right at the vertex that it should be at. Okay. I'm drawing it small, I guess, because I want to do several of these. And I also want to note, oh, come on. A nice fact is that I have an action of the cyclic group of order 2 on this well, on the tree, I guess, but in particular on the lift of the vertex that I've chosen, such that the quotient looks like my graph gamma. So that will continue to hold throughout this process. Okay, so I need to do the same thing here. So what I will do is I will give myself another copy of gamma, and I will glue it in at the vertex like so. Okay, I'm going to make this smaller. Can I make it smaller? I guess not. Smaller. Turn. Oh, I lost it. Okay, I'll try one more time. Turn. Shrink. Perfect. Up. I'm going to say that that's fine. Great. Okay, so I need to do the same thing for the orange and the green edge. So for the green edge, I do this. And for the orange edge, I do this. Great. And then now what we can observe is that I've made the observation true for all of the vertices that belonged to my original copy of gamma. So this was my original copy of gamma. I'm highlighting it. And at each of those, I do have the stabilizer of the vertex equivariant bijection with the star of that vertex as I need it. And so what I would do to continue building the tree would be just to do this everywhere, right? So I need another, for example, I need another copy of gamma at this vertex and at this vertex and at this vertex and so on and so forth. And so you can kind of imagine how it would look if I continue to build this tree up from these pieces. In my thesis, I call the basic piece that we're building things out of, I call them puzzle pieces, which is not, I don't know, a term that exists anywhere else, but I thought of it as kind of useful as a way of thinking about what's going on. Okay, any questions so far with this free, I guess, trivial edge stabilizers action? Okay, great. So we're gonna do the same thing, but we're gonna add one layer of difficulty. We're just gonna get rid of this assumption that the edge stabilizers are trivial. Okay, so in this case, my graph gamma will still be a tree, but I'm gonna allow non-trivial edge groups. So here,
Rylee, sorry.
Sorry. Go ahead.
So we have 2 questions / comments. Hanglu doesn't get why it doesn't get the degree 4 vertex. She thought the vertices had to have degree 2 for C2.
That's a good question. What was the other question?
And Hannah was just saying that she's confused about how the pieces go together.
Yeah. Okay, cool. So let me talk through it one more time. So each of these pieces looks like this this guy right here that I've highlighted. So it has 4 edges, a red edge, a blue edge, an orange edge, and a green edge. And I'm going to think of it as kind of like a Lego. And the graph groups downstairs is going to tell me how to attach my Legos together. So what I'm going to think about is every time I see a vertex with non-trivial vertex group, that's like saying, here's a place where I can attach Legos. And what it wants to do is it wants me to attach a Lego for each element of the group in this case. Okay, so this is a cyclic group of order 2. So I need 2 Legos attached to that vertex. So like so. So the valence 4 vertex, actually, it's the same principle. It's just interesting because this vertex is sort of in the interior of the graph. So there are still 2 Legos. There's the original Lego, and then there's the Ego that I have attached here. Yeah?
But sorry, can I just unmute myself? Is that okay?
Yep, yeah.
I'm confused about the orientations of the pink and the blue. Like it has 2 pink coming in and 2 blue going out.
Oh, I see.
Should that be rotated or something so that there's one of each?
I think no. What it is, I see why it is confusing because it's the kind of the opposite of what you would do to construct the universal cover of like a normal graph. But in this case, what I want also is I want the action of this cyclic group of order 2. This cyclic group of order 2, it should also preserve the orientations of the edges incident to it. So it should preserve the colors and the orientations. So it should send a blue edge going out to a blue edge going out.
Okay, cool.
Yeah, so it's a little bit different from what we're used to. And then, okay, so this is the inductive process. The only thing that I need to insist on is that I never make any loops, right? I want it to be a tree. A tree is a graph with no loops. Just don't put in any loops. Excellent. Okay, cool. Let's do it with edge groups.
So George has a question. He asks, if you swap the orientation of the blue edge, would you then not need to glue something in that vertex?
As in, if I were to have the orientation look like this.
He says yes.
I see. This is really a question about this definition. This is my cheater way of saying, remember, every edge, we're thinking of edges as like, intervals. Every edge has 2 orientations. And so when I say oriented edges, I mean an edge together with its orientation. So when it was like how it was before, like this, the edge that had terminal vertex, this guy right here, was really the blue edge with the opposite orientation. That's fine. I could have done it without orientations as well, but I think it's, when there are loops, it will be nice to have orientations. Okay, let's try it one level of difficulty higher. This is actually the only place where it genuinely gets more difficult. The final case, the general case, there'll be a cheap trick. So the idea is basically the same. I'm still going to use my graph gamma as my basic piece, but the rules for gluing will be slightly different. Okay, so let me copy my basic piece. Oh, I got a letter C as well. Today is brought to you by the letter C. Okay, so this is my basic piece. Let me just sort of talk you through a couple of steps in the process. So the vertex on the right has the vertex group cyclic of order 2. So I need 2 copies of my basic piece, and I'll just glue them in exactly as before. For this middle vertex right here, its vertex group is cyclic of order 6. So a priori, I need 6 copies of my basic piece all glued in at that vertex. And morally, there will be 6, but we're going to see that there's going to be a little bit of a wrinkle. So the wrinkle is the following. This red edge has an edge group. It's cyclic of order 2. So remember what I said earlier was that the set of red edges lying above this edge in the tree should be the set of cosets of the cyclic group of order 2 inside the cyclic group of order 6. What that means is there should be 3 red edges and not 6. So I'm going to glue in 6 copies of my basic piece, but some of them I will secretly drop the red edge and just use this original red edge from before, or use one of its other friends. So let me glue in one of these where I do have a new red edge. Okay. And let me do the other one where I do have a new red edge. Maybe it looks like this. Okay. And then for the other ones, there's secretly a red edge, but it's actually one of the ones that we've already glued in because the coset is sort of eating it up. And so what I will do is I will just attach the new blue edges as well. What you should think about really is that, so my basic piece is the same, and the tree will still be sort of tiled by these basic pieces. But what will be the case instead will be that the tiles overlap. And the tiles will overlap exactly in the pattern of like the set of cosets of the cyclic group of order 2 inside the cyclic group of order 6. So for example, this is a basic piece, but maybe this is also one, okay? And I will still get an action of the cyclic group of order 6 on this vertex. It will act freely on the set of blue edges, and on the set of red edges, it will act like the action of the cyclic group of order 6 on its set of cosets for the cyclic group of order 2 inside it. Okay, fine. Slightly confusing, but fine, hopefully. Okay, so this edge group also includes into the cyclic group of order 4, which is my my last vertex that I need to take care of. And the set of cosets of the cyclic group of order 2 inside the cyclic group of order 4 has size 2. So there are 2 cosets. So I only need to attach one new die. Okay. So notice, I guess, even though this cyclic group of order 2 doesn't see this blue edge, I don't attach 4 blue edges. Sort of, I don't. What I don't do is the following thing. I don't put in like secretly another blue edge there to like make up for it. No, I only want my vertex group to see what's going on at the vertex itself. Okay, so then the idea is basically still the same. I just do this everywhere. So every time I see one of these vertices, I just add another copy of my basic piece on the other side. Every time I see one of these vertices, I add 6 of my basic pieces, but 3 of the red edges are actually, what am I really saying? The red edges come in pairs, basically by the patterns of the cosets of the cyclic group of order 6. Sorry, the cosets of this guy and this guy. And then the same thing is true over here. I will add one new guy corresponding to the 2 cosets of the cyclic group of order 2 inside the cyclic group of order 4. So this, I guess what I'm saying is that in the end, this tree will have 3 orbits of vertices, as we said before. The orbit corresponding to this guy will have valence 2 in the tree everywhere. So like this guy right here has valence 2. This guy will have valence, I guess, 3 plus 6 equals 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And this guy will have valence 2 as well. And so really, so the key fact that I'm using here is that if you remove a vertex of a tree, you disconnect it as a topological space. So what I'm really doing is I maybe for this vertex in the middle, maybe I have two basic pieces. I have the left-hand basic piece, which consists of the red edge, and the right-hand basic piece, which consists of the blue edge. And I'm treating them separately according to the pattern of left cosets of the edge group inside the corresponding vertex group. That's the idea. Cool. Okay, so that was the hard part. Are there questions?
There are some questions and comments. I mean, they're along the lines of like, is it what's intuitively what's the appropriate way of thinking of each CN? Is it like proper to think about it as a zoomed out copy of the Kitty graph, or maybe a space whose fundamental group is that?
Both of those are great. The nice thing about graphs and trees is that if you want a group to act on, like say a tree with a fixed vertex and fix that vertex, there's basically only one action that you can do. And it's kind of the left multiplication of the group on itself. That's kind of really what we're doing here. So yeah, we will in a second come back to like thinking of this guy as like maybe a space with fundamental group cyclic of order 6. But for now, I think just think about it as, okay, if I wanted to act on a tree, there's basically only one way that I could do it, and it has to look something like this. Okay, let's do the general case. So the general case is cheating. I love it. So what you want to do is if your graph has non-trivial ordinary fundamental group, what you want to do first is construct the universal cover of that graph. Okay, so for example, this guy is a loop, so it has fundamental group infinite cyclic. And what I want to do as my basic piece is I want to construct the universal cover of it as a graph. So it will be some sort of infinite line divided into vertices and edges. Okay, so it goes off maybe infinite like so. Maybe I'll orient the edges. Okay. And what I want to do is I want to turn this universal cover into itself a graph of groups. And I'm going to do so in the simplest way possible. What I will do is I will just set the vertex group of any vertex in the universal cover to be isomorphic to the vertex group downstairs. So for example, this group, this vertex V had a vertex group infinite cyclic. So this vertex will as well as this vertex, and so on and so forth. All of the vertices will have vertex group infinite cyclic. I'll do the same thing for the edge groups. So this edge right here had edge group infinite cyclic. So this edge will also have infinite cyclic edge group, and so will all of the other edges in my basic piece. Okay, and then what I want to do is I want to treat this as a graph of groups, and I want to apply my strategy from the previous slides. Okay, so let's talk through this example carefully. So this edge group is infinite cyclic. I wrote it as being generated by an element B. And what I know is that there are homomorphisms, right? Inclusions of this edge group into this vertex group. And one of them will be an isomorphism. It will just send B to A. The other one will send B to A squared. So it will realize that other infinite cyclic group as a index 2 subgroup of the vertex group. So what that means is what? Oh, I guess it means the following thing. So I need to have my basic piece, and then I'm gonna sort of start gluing in copies of it according to the pattern of cosets. So since the, oh, I didn't want to do that, but can I paste it? Excellent. Since the, if I look at the inclusion of the edge group backwards into the vertex group, that's an isomorphism. So there should only be one, at each vertex, there should be one red edge leaving it. But if I look at the inclusion of the edge sort of forwards into the vertex group, that's an index 2 subgroup. So there should be 2 incoming edges and 1 outgoing edge. So this tree that we're going to build will be trivalent, and it will look something like this. Okay, so I need 2 edges coming in for every edge coming out. So 2 edges coming in, and then I said 1 edge coming out, so I'm just going to erase this edge, or actually this whole half line. Okay, and then I will do the same thing at the next stage. Turn, excellent. So I have 2 edges coming in, and now I have 1 edge going out, and then 2 edges coming in. Whoop. 2 edges coming in. Perfect. Ah, come back. Turn. Great. This is the one thing that Notability is not as good at, or maybe it's just me. And 1 edge going out. And so this tree is kind of interesting. It's kind of like there's like a preferred way to go off to infinity in this tree. And every piece of it is sort of like eventually joining up with it, but only after a potentially really long time. 2 edges coming in and 1 edge going out. And then there should be another one here, I guess. So I'll just draw it or add it. Okay, 2 edges coming in and 1 edge going out. So this is kind of cute. So how does the vertex group act on its lift? So I have an action of the infinite cyclic group on sort of a local action on the edges incident to this vertex right here. And what it does is it fixes this edge. This edge gets sent to itself. But the edges coming in are swapped basically by the action of z on z mod 2z, or the action, in other words, of z on the set of cosets of 2z inside it. Cool. And so really what I should do is I should draw this picture everywhere. Like, for example, this guy, each of these guys should sort of branch off backwards. So there should be somebody going out here and out here and out here and so on and so forth forever. This is very cute, I think. So it turns out that the fundamental group of this graph of groups is one of the groups that we guessed yesterday. It's the BS12. So it's the Bomsog solitaire group 1, 2. We'll compute its fundamental group, or we'll compute this later on in this talk. Great. So far, so good. So that's what the Bestvina tree looks like. And the idea for constructing the group is that you're just kind of going to piece together each of these local group actions into a global group action. But I think the better way to think about it is as a fundamental group. So what's the fundamental group? It's a group of homotopy classes of loops in my space. So what I'm going to do is define a new notion of what a loop in a graph of groups is, define what homotopy means for them, and then just set that to be the fundamental group. Great. So let's do it. Oh, but first, so this is something that I owe, I don't know, maybe the more traditional topologists in the audience / Robert Kropholler. It's graphs of spaces. So a reference for this perspective is a paper of Scott and Wall called topological methods in group theory. And it's from the like 60s or 70s. I heard somebody in my purview say that this is the modern perspective on graphs of groups, and I strenuously disagree, but I guess that's fine. So if you have a graph of groups, so same notation as before, what I want to do is for each vertex, I want to choose a space, any old space, with fundamental group isomorphic to that vertex group. And then for each edge, I want to do the same thing. So I want to choose a space with fundamental group isomorphic to the edge group. And then I also want to have maps of spaces from my edge group into the corresponding edge space into the vertex spaces that are incident to the edge, such that the induced map on the level of fundamental groups is the group homomorphisms that are part of the definition of a graph of groups. Okay. So a general construction, when you have something like this, if you have a map from X to Y, you can form its mapping cylinder. And what that is as a space, I guess it's the disjoint union of Y on the one hand with X cross an interval. So I'll write it as X cross I for interval, with modulo the equivalence relation that says that I guess X comma 1, I'm going to set that to be equivalent to, so maybe I'll just erase this and move this over. X comma 1 is going to be equivalent to f of X in Y. So it's kind of like you have your space X and your space Y, and you have a map, and you're just kind of gluing in a copy of X cross the interval via the map. Okay. If you've heard of a mapping torus, this is sort of a similar idea. So that's the mapping cylinder. So a graph of spaces will be built from mapping cylinders in the following way. So what we're going to do is we're going to form, okay, so this is a lot of notation. For each edge in my graph, I'm going to form the mapping cylinder of, oh, sorry, this is oriented. Okay, so I'm cheating. Each edge counts twice. So I'm going to have the mapping cylinder of the map from the edge space to the target terminal vertex space. And I'm going to form that mapping cylinder. And then I'm going to mod out by an equivalence relation. So what I'm going to do is I'm going to set each copy of the base space, so the vertex space, so X sub V in M sub Fe is identified. So I guess what I'm kind of doing is I'm forming sort of like a multiple mapping cylinder. So if I have two maps in, like maybe I'll just glue in the other one like this, but I want just one copy of my target space. Okay. Or you could think of it as two mapping cylinders, and then I've just identified the target spaces by the identity. That's fine. And then I want to glue the edge spaces. So this part of the edge space, I want to glue it to the corresponding edge space for the edge with the orientation reversed. And I also want to glue by just the identity. I don't want to do anything fancy with it. Okay. So each copy of X sub V and M sub Fe is identified with, I guess, together. Same with X sub E cross 0. Okay, so I'm going to do the example for the graph of groups that we just did. It's going to look like this. So my X sub V will be a circle. So X sub V is S1. It's not a great circle. I can do better. Perfect. And then X sub E will be also a circle. maybe an ellipse. I guess that's fine. And then the two maps, I guess I have FE and FE bar. This will be just the identity, and this will be a twofold cover. You can check that that will have the correct images on fundamental groups. And then what I'm saying is that the graph of spaces will look like, well, I guess it'll look like a circle. And then there'll be sort of a cylinder mapping in two ways. Whoop. Two ways. This way will be by the identity, and this way will be a twofold cover. So it'll look like it'll be kind of like a cylinder, except that when you come back, it'll be you'll kind of wrap around twice. Okay. A useful fact that Robert Kropholler likes is that the universal cover of this graph of spaces X, so I wrote it as X tilde, it has a map to the Serre tree. Really all it does is it sends each like sort of interval part. It's like the projection onto the interval part of each mapping cylinder, and it collapses each edge space to a point and each vertex space to a point. That's the map. And it's a theorem that I won't prove, but is true, is that graphs of aspherical spaces are aspherical. Or in other words, what that's saying is that if each of these vertex spaces and edge spaces have contractible universal covers, so for example, the circle, then the graph of spaces itself has a contractible universal cover. The idea roughly being that you can just contract it in each edge space and each vertex space, and then contract the tree, because we know that trees are contractible.
So Rylee, we have a question. And the question is, so there is a map between the edge group and the vertex group. Shouldn't the space mapping be in the opposite direction?
There's a map from the edge group to the vertex group.
Mm-hmm.
Sorry, I don't think I understand. Let me see what the chat says. There's a map between the edge group and the vertex group. The space mapping should go from edge group into vertex group because the group mapping goes from edge group to vertex group. Yeah, so it's like it's a covariant functor. So edge space into vertex space because edge group into vertex group. That's the idea. Oh my goodness, why did you get me to say the word covariant? I'm terrible. Okay, so that's our useful aside. One way to think about graphs of groups, this is a way that I dislike, is that it's just sort of a helpful abstraction to keep track of paths in the graph of spaces and homotopies between them. MFE, yeah, so this is supposed to be the mapping cylinder. Cylinder of F sub E from the edge space into the vertex space. Cool. Great. Okay, so the fundamental group. We love fundamental groups. Let's define a fundamental group. Okay, so a path in a graph of groups is going to be sort of, we're going to think about it slightly combinatorially. You could think about this purely topologically, but it's better to walk before you run. So we're going to walk. So combinatorially, a path is a finite sequence of the following form. So it's going to look like G0, E1, G1, E2, G2, E3. So it's going to alternate between edges and elements. So each GI belongs to a vertex group, the ith vertex group. So these are these vertices. There's another one. And each G is going to belong to the corresponding vertex group. And I guess what we want really is that for these edges to genuinely connect the the corresponding vertices in the graph. So this is a true picture, i.e. The terminal vertex of E sub I is the initial vertex of E sub I plus 1. Okay, so far so good. So if I have such a path, I can invert it in quotes, just by inverting each group element and reversing the path. And so doing those together. So if I had G naught E1, blah, 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 to En Gn, its inverse would be Gn inverse En bar, blah, 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 E1 bar, G naught inverse. Okay, great. So I'm going to say that two paths are homotopic rel endpoints if one can be transformed into the other via a finite sequence of moves of the following kind. So we can add or subtract the composition of a path with its inverse. Great. So I guess sigma a path. And you have to be able to add it, you know, it has to be a path, right? Like I can't just sort of add hanging off in space and edge its reverse. Don't do anything silly. Okay, and then the other thing that I'm allowed to do is I'm allowed to move elements of the edge group sort of past the edge. So what I'm saying is if I have H in my edge group G sub E, I can replace let's see, E followed by the inclusion of H into its terminal vertex group. I can replace it with having the edge group element first. So the inclusion of my edge group element H into its initial vertex group. So that's this iota E bar E. Okay, so I can kind of push group elements along the path, but only if they belong to the corresponding edge group, or they belong to the image rather of the corresponding edge group. Okay, so that's not so bad. Great, and then more general things. So what's a loop? It should be a loop if the underlying path of the edge path is a loop. So the initial vertex of my path is equal to its terminal vertex. And it's going to be based at, you know, the initial vertex or which is equal to the terminal vertex. Okay. So the fundamental group of my graph of groups based at the point P is the group of homotopy classes in the sense of the previous slide of loops based at P. And the operation is just going to be concatenation like usual. Okay. So a little bit of common terminology is we say that a graph of groups is a splitting of its fundamental group if the fundamental group is not equal to any vertex group in the graph of groups. So in some sense, what I'm saying is that the fundamental group is bigger than any of its vertex groups. And we say that a group splits if it admits a splitting. Not so bad. Okay, cool. So what I'm going to do is tell you a theorem for computing fundamental groups. And maybe I'll just do an example of what a covering map looks like rather than subjecting you to pseudo-natural transformations, which is a terrible, scary thing. Anyway, so the fundamental group of the graph of groups has the following presentation. So what we're going to do, what's a good example? Oh, let's do my favorite one from earlier. So here's my graph of groups. It has a graph, a tree. I don't know why I'm drawing the edges so terribly. This vertex is cyclic group of order 2, 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 trivial group, and then all of the edge groups are going to be trivial. Okay, so what I want to do is I want to pick a spanning tree inside my graph. So I want a subtree of my graph that contains every vertex. Since this graph is a tree, its spanning tree is itself. That's fine. And I'm going to, the theorem, I guess, says that the fundamental group of the graph of groups, oh, I guess I also want P belongs to T naught. that's automatic if P is a vertex, but P does not have to be a vertex. So my fundamental group of my graph of groups is going to be the quotient of the following thing. It's going to be the free product of the vertex groups with a free group on the set of oriented edges. I'm just saying oriented edges to be, I don't know, pedantic, I suppose, by the normal subgroup that basically what it does is it imposes the following relations. It says that if you reverse an edge, you invert the corresponding group element, right? If your edge belongs to your spanning tree, then its image in the fundamental group is trivial. So in other words, none of these edges can contribute anything to the fundamental group just because they belong to my spanning tree. And then finally, I have the same relation that we had that sort of performed homotopy between our paths, where we could sort of pull elements of edge groups sort of across the corresponding edge. I'm going to sort of define that to be true algebraically in my group as well. Okay, so these are my relations. And the theorem says that this computes a presentation for my fundamental group of my graph of groups, which is kind of nice. It tells you that, I don't know, I guess if you know group presentations for each of your vertex groups, then you know a presentation for the fundamental group of the graph of groups as well. It also tells you that, I guess corollary, each vertex group injects into the corresponding fundamental group. This is very nice, and it's not true in generalizations of this theory to higher dimensions, but this is a nice fact to have. Okay, so for example, this example, I killed every edge because every edge belonged to my spanning tree. So I guess all I have at this stage is the free product of 4 copies of a cyclic group of order 2. And then if I check, none of these relations say anything about this particular graph of groups. So this has fundamental group isomorphic to the free product of 4 copies of the cyclic group of order 2. I like to call this group W4, but nobody cares. It's fine. Great.
Rylee, there is a couple of questions. So first is
Van Kampen's theorem.
So Nathan first asked, is it true that paths don't really see the edge of the edge groups?
Yeah, the elements of the edge groups are kind of ghostly. You really only see their images in the corresponding vertex groups. And that's kind of why I've been, I don't know, I've been kind of treating them sort of carefully. Like every time I have an element of an edge group, you're always seeing it applied to, like I'm always applying the inclusion into one of the vertex groups. Oh, yep, no, actually. The point is that everything in T naught is gonna die from this free product, or this free group rather. So if I wanted to be more economical, I guess I could say the free group on the set, the complement of T naught in gamma. If you use, is there a sort of Van Kampen theorem for these fundamental groups? Yeah, there sort of is. If you use the graph of spaces definition, then for sure, for example, something like this, you could just use Van Kampen's theorem directly. There are examples on my next slide where you can't use the normal Van Kampen's theorem directly, but nonetheless, our graphs of groups knowledge does apply. And so kind of what you would want to do is take you would want to do it in kind of 2 stages. Like, remember how last time, like when we were building the Bestvina tree, what I said is that if the graph itself had non-trivial fundamental group, you first take the universal cover of the graph and then treat that as a graph of groups. You could do that the same thing for the graph of spaces definition as well. What happens when you have a non-trivial trivalent vertex group? I don't understand. Let me compute some examples, okay? So what we already said in the previous slide is that this has fundamental group, I guess the free product of 4 copies of the cyclic group of order 2. This group right here that we had earlier. Okay, so it's the quotient of the free product of, so it's the free product of Z with Z. Remember one of the, well, okay. Z with F2, let's say. Okay, so the Z is coming from this vertex group. The F2 is coming from the edge E and its inverse. And then I'm modding out by the relations that say that, I guess E inverse equals E bar. Okay, that's fine enough. I also want, I guess the spanning tree is trivial, so there's nothing dies from that. But I also want that E with the inclusion of IE bar, no, it should be IE of B is equal to IE bar of B followed by E. Let me erase my surface and say in more words what that means. So I sub E of B is A squared. So what we're saying is that E A squared is equal to IE bar of B is A E. Or in other words, I could rewrite this as saying that A squared is equal to E inverse AE. Okay, and this is the formula for Baum-Sachs-Solothurn groups in general. So the Baum-Sachs-Solothurn group M comma N has the presentation. I'll use the same notation. So A and E subject to the one defining a relation that says that E will conjugate A to the M to A to the N. Okay, so you can check, but if you replace M comma N with 1 comma 2, that we get what we just had. And also, I guess we have that, I guess BS11 is Z2. And BS1 minus 1 is the Klein-Bottle group. And then in other cases, the group is a little bit weirder. Great, good. Oh, I guess the other, let me also say another thing about this particular example. If you have a graph of groups with underlying graph a loop with one edge, like here, the corresponding group is called an HNN extension with, or I guess, and I guess you write it as G sub V, so the vertex group, and then you write the free product asterisk, and then you subscript, I don't know why, the edge group. So in other words, the Baum-Sachs-Solothurn groups, you could write them too succinctly as so they're sort of Z, HNN extension of Z.
So a question.
Yeah.
So is there a, so it's in the chat. So is there a coincides relationship between the graph of spaces for T and the graph of spaces for gamma?
As in, if I have a graph of groups and I build the corresponding graph of spaces, okay, so I can do that thing. And then I take the universal cover of each of these things. So here I'm going to take the Serre tree. And here I'm going to take the ordinary universal cover of this graph of spaces. Just as there was a map from this graph of spaces downstairs to my graph, just by sort of forgetting everything about the vertex or edge spaces and just saying, okay, do I belong to the edge space for E? Then I'm going to map into the edge E. Okay, so that was the map down here. The map upstairs is exactly the same. I have I guess it turns out that the universal cover has this nice sort of, it looks like this. Let me give myself a new page. Copy, paste. Okay, here's my new page. Let me erase everything. So the universal cover of the graph of spaces has the nice description as follows. I guess, so if you have your tree, looks like this, blah, 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 blah. So this is sort of supposed to be T, and this is supposed to be the graph of spaces or the universal cover of it. It has kind of like a blocky feeling to it. So this blob, all spaces are blobs. So if this is a vertex V, or I guess V tilde, this space will be homeomorphic to the vertex space for V, but actually it's a universal cover. Okay, and then for each edge, I will have sort of a the universal cover of the edge space cross an interval in my universal cover X tilde. And it's turtles all the way down. That's exactly what this space will look like. Yeah, I hope that's helpful. There's a picture of the key. Yeah, so if you do it for the particular example of the S12, I guess this space will be a line because it's the universal cover of a circle. This space will be a rectangle, and there will be a rectangle for each, or I guess an infinite strip really, and there will be a rectangle for each edge in the tree. So the space will be sort of like it'll be made of kind of sheets of strips in like kind of a trivalent tree-like way. Cool. Oh, and then I guess if you look on Wikipedia for the Bohm-Zach-Solitar group, you'll see that there's kind of like either an expansion or a contraction of kind of how the cellulation of the, right, what am I saying? The universal cover of a circle, thought of as a graph, has a natural cell structure where it's like if you cellulate R by putting cell like vertices at integer coordinates. And what I'm saying is that the Bohm-Zach-Solitar group will sort of have like a doubling or a halving of that cell structure in the universal cover of the graph of spaces. Okay, maybe I shouldn't erase that. I'll just leave it in. Okay. Okay, so HNN extension. By the way, this confused me for 3 years. HNN is, it doesn't stand for anything really. It's just Higman, Neumann, and Neumann. So it's just 3 people's names. They're I guess an author of a paper that first sort of introduced and studied properties of these groups. If you have a graph of groups with 1 edge and 2 vertices, then the fundamental group is going to be the amalgamated free product of the 2 vertex groups amalgamated along the edge group, and really amalgamated along the inclusion of the edge group into the vertex groups, right? Both of these things are sort of, these notations are kind of underdetermined. Somebody comments, yeah, the Neumann family is very important in geometric theory. That's very true. Oh, I'm out of time. I'm totally out of time. But let me just draw the genus 2 surface and observe the following cute fact, which says that the fundamental group of the graph of groups corresponding to cutting the surface along that simple closed curve is, I guess it's an HNI extension of a free group of, what's the correct rank? I guess it's 3 because it's a 2-hold torus. a two-hole torus is fundamental group free of rank 3, and it's an H&N extension along a Z. I don't know, I said Z. One of the inclusions is, I guess, gamma, which is a generator of F3. And then the other inclusion is a commutator of, I guess it's the product of the other generators, their commutator, with, let's say, gamma as well. And if you write down what that what the relator for that H&N extension looks like, it will look like the following thing. So if I'm going to add a new letter. I'm going to call it T, and it will say that T gamma T inverse is going to be equal to, I think I want it to be gamma times, so I'm going to say gamma inverse, times the commutator of the other two generators inverse. And that looks like kind of a mess. And in fact, I think it's slightly wrong. I think I want to have gamma on the other side because I know how inverting group elements works. But what you'll see is if you put everything in this onto one side, you'll see the usual product of commutators presentation for the fundamental group of the surface of genus 2. Yeah, so I think that's all I'd like to tell you today. Thank you for listening.